Hi, it's Mr. Mac, and we're going to be looking at dynamics, and this is our second video in the series as you're following the slides. And we'll see a lot about forces and acceleration and a little bit about energy.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's Physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
We're looking at dynamics, and here is Nicholas Kay as he's shooting in the Commonwealth Games basketball against the New Zealand team. We're learning to apply laws of motion and the conservation of energy to the analysis of motion, and we'll be able to explain and analyse situations involving forces, acceleration and energy. Here are the NISA outcomes that they want students to fulfill. Well, let's look at the types of forces. There are actually 4 fundamental forces in the universe, and in ascending order of strength, there's gravity force, nuclear weak force, electromagnetic force, and nuclear strong force. You will need to know that all the way through. An interaction involves a particular physical mechanism that occurs between 2 different objects. And so some examples of that interaction, of contact forces, are friction, and we'll look at static friction and kinetic friction, but there's also rolling motion friction. Another example is normal force, which is perpendicular to the surface of contact. And here's a great diagram I found showing the compressed molecular bonds as they push upward on an object to show the normal force. Well, here's our worked example to do with the coefficient of friction. A motor is used to pull a 50 kilogram block up a 10 meter long incline as shown in the diagram, and it's 6 meters high and 8 meters in horizontal distance. And the coefficient of friction, that's kinetic friction as it moves, between the block and the incline is 0.70. And the question is, what is the tension T in the rope if the block is moving at a constant speed? First step is always data. M, the mass, is 50 kilograms. G, the acceleration due to gravity, is 9.8 meters per second squared downwards. We have the side opposite the angle in this right angle triangle is 6 meters. The adjacent side is 8 meters. And the hypotenuse, which is the ramp, 10 meters. Mu, that's the Greek letter mu, we're going to use that for the coefficient of friction, is 0.7. It doesn't have any units. And we're going to draw a free body diagram. Now the acceleration is 0 because it's moving at a constant speed. Therefore, the net force acting on this block is also 0. When we add the forces together, we have T minus the force due to friction and minus the weight in the x direction must be 0. That is T equals the force of friction plus W sine theta. Just using trigonometry, W, the weight in the x direction, is W sine theta. So W equals mg, which is 50 times 9.8 or 490 newtons. Wx, so that's the component of the weight in the x direction. Remember, x is down the ramp, is W sine theta. So it's 490 times 6 over 10, which is 294 newtons. The force in the normal direction, that's in the y direction at right angles to the x direction, is W cos theta, which equals 490 times 8 on 10, which equals 392 newtons. And so the force due to friction must be the mu coefficient times the force in the normal direction. Mu is 0.7, force in the normal direction we've just found out is 392. Multiply them together, you get 274.4 newtons. Therefore, the tension equals 274.4 plus 294, which is 568.4 newton. Let's now look at worked example 11. Here's a person riding on a skateboard, rolling at a constant velocity horizontally for 8 meters, carrying a bucket of water with a vertical force of 10 newtons just to hold that bucket up. How much work does he do? Well, here's the first step, data. Force in the y direction, he's lifting that bucket, he's holding it, 10 newtons. The distance travelled is 8 meters in the horizontal direction, and we want to find the work. Well, we need to choose from these two formulas on the formula sheet. Work equals force in the parallel direction times displacement. Or we've got, if there's an angle involved, work equals Fs cos theta. Well, let's choose work equals Fs cos theta. But in this case, the angle is 90 degrees because he's lifting in the vertical direction and his motion is in the horizontal direction. So the work equals 10 times 8 cos 90 degrees, which of course is 0 because cos of 90 is 0. So there is actually no work being done by the force carrying the bucket, since it has no component in the direction of motion. Here's another worked example dealing with work. How much work do you do on an object of weight mg as you lift it? A displacement of h straight up. And how much work if you lowered it the same distance? So there's a cartoon of a person lifting, there's a diagram of a person lifting. You can see h is the height from the ground. First step, draw a diagram, which I've done. To lift the object, you must pull on it with a force equal to its weight. And the displacement upwards, S, and the lifting force is in the same direction. So W, work, equals Fs cos theta, with theta in this case being 0. And work is F is mg, that's the weight, times h cos theta. Now cos theta, or cos of 0, is 1. So we now end up with work equals mass times g times h. So the work done against gravity when you lower the object, and F and S are in the opposite directions, must be negative mgh. So the work you do as you lift, mass times g times h. The work you do as you lower it, doesn't matter how gently or what path you take, the work is negative mgh. Here's worked example 13. A 30 kilogram box is pulled along the floor at a constant speed by a force F acting at an angle of 37 degrees. The friction force of 20 newtons, that's kinetic friction, is opposing the motion. The question is, find the work done by the pulling force as the box is moved 5 meters. First step, of course, draw a diagram. There it is. And the diagram will help you sort out all the factors involved. So the acceleration being 0 implies that the net force is also 0. So the net force on the box is 0. It's not moving. It's not accelerating. It's pulled across at a constant speed. Therefore, the forces in the x direction must be balanced. So we have Fx equals F cos theta, which equals the negative of the F due to kinetic friction. So F cos 37 must equal 20 newtons. Ignoring the sign, we're just going to equate those two. And to find the work done, we use W equals F parallel S. Now, since the force in the x direction is 20 newtons, the work done is 20 times 5, which is 100 newton meters, or 100 joules. Now, is it necessary to know the mass of the box to solve this problem? Have a think about that one. Think where we've used mass in this case. Let's derive kinetic energy. It can be simply derived. We start with the work formula and then add Newton's second law of motion, and finally the v squared equation of motion. Work, we know, is given by W equals force in the same direction as displacement. So multiply them. From Newton's second law, we know that the net force equals mass times acceleration, F equals ma. So work must be ma times s, provided that the acceleration and the displacement are in the same direction. Using the motion equation v squared equals u squared plus 2as, we can rearrange it as a equals v squared minus u squared all over 2s, which we can now substitute into the work equation. So instead of MAS, we now have M brackets v squared minus u squared all over 2s times s. And you'll notice that the s's cancel. And 2 is on the bottom line, so it's a half mv squared minus a half mu squared, which shows how much work a moving object can do as it slows from velocity u, the initial velocity, to a velocity v. So the work done is half mv squared minus a half mu squared. So the energy of an object is due to its motion. That, by the way, is also known as the work energy theorem. Example 4. A 2-ton car is travelling at 72 kilometres per hour. It coasts to a rest on level ground in 100 metres. How large is the average friction force acting to stop the car? First step is data. So the net force in this case is only the force due to friction in the horizontal direction. It's the only force acting on the car in that direction. U is 20 meters per second, V is 0, and our displacement is 100 meters. From the work energy theorem, the change in kinetic energy is the work done by friction. So delta kinetic energy equals work due to friction. So half mv squared minus a half mu squared equals force of friction times s cos theta. So 0 is the final velocity, so it's got no kinetic energy when it stops. Minus a half times 2000 times 20 squared equals force due to friction times 100, that's the displacement, times cos 180 degrees. It's acting in exactly the opposite direction. And when we sort out the signs and do the calculations, force due to friction is 4,000 newtons. And here's worked example 15 to do with kinetic energy. If the friction force on the car is constant at 4,000 newtons, how fast will the car be going after 50 meters? Well, here's the data. We know that the net force in the horizontal direction is due to friction. Initial velocity is 20, and the displacement in this case is 50. We want to find the final velocity. From the work energy theorem, the change in kinetic energy is equal to the work done, in this case by friction. So delta Ke equals Wf. So a half mv squared minus a half mu squared equals force due to friction times displacement times cos theta. And again, theta in this case is 180 degrees. But this time we need to substitute carefully, for we know the force due to friction, we know the displacement, we know the initial velocity is 20 meters per second, we know the mass. The only thing we don't know is v. So let's rearrange and calculate to get v squared equals 200 or v equals 14.1 meters per second in the positive direction. So it's still going forwards, but it's slowed down. So we've seen some worked examples about forces and acceleration and energy. In our next video, we'll be applying that to momentum and collisions. I'm Mr. Mac. Thanks for watching.